Thank you, sir. I appreciate that. We both work at CERT in the vulnerability analysis team. My name is Madison Oliver. I've been interning at CERT for about a year. I'm in my second year at Carnegie Mellon in the Heinz College studying information security policy and management. It's quite a mouthful.
I'm Kyle O'Meara. I've been at SCI now, CERT, for about 2.5 years, and before that I was with FireEye and started off my career at NSA. For those that don't know what SCI is, right, so we're the research and development arm that focuses on cyber for the Department of Defense. Where Madison and I sit in the directive is that we're in CERT, we're in the threat analysis directive, and on the vulnerability analysis team, and then specifically attack modeling, right? So we have sub-teams of overall arching teams. But we're gonna, go over our framework for embedded device vulnerability analysis.
So the agenda for this presentation is pretty obvious as follows. We'll give you guys a brief introduction and the motivation behind writing this paper. I feel like I can't get too close to the other microphones. We'll discuss the framework that we created and share our results with you of actually applying this framework to an embedded device, go through future work that can be done to better improve this research, and then a brief conclusion. That's fine. I'll manage. So as I'm pretty sure all of you know, embedded devices are becoming significantly more ubiquitous and readily accessible to the average consumer. Embedded devices are more or less everywhere now, and they're going to continue doing so. As device popularity increases, vulnerability research about these devices should hopefully and ideally will be increasing too. So there isn't a clear process when you're researching embedded devices. There's no like step-by-step, here's what I should do, here's what I should be sure to look at. Everyone kind of just does it as they see fit and like hopes for the best that they have caught everything. So the framework that we're proposing is a concrete scientific process, a nice step-by-step, relatively easy to follow process, I hope, to thoroughly complete research in vulnerability analysis on embedded devices. Our motivation behind creating this paper was giving other vulnerability researchers a way to create comparable and thorough results so they can actually do something with the results that they get. And we wanted to ensure that every single component of the device was researched at least at the most basic level. A lot of the time in research, especially embedded device research, it's very easy to get bogged down and only focus on one aspect of it. And these devices are so complex that there is a lot more that could be missed. So we hope that our framework would prevent that from happening. The framework that we are proposing has these phases. It starts with embedded device list curation, information gathering, firmware analysis, web application analysis, mobile application analysis, hardware analysis, and then obviously vulnerability analysis. So we're going to go through each of these steps in detail, starting with embedded device list curation. So this was something that we had to do, obviously, to come up with a device to test this framework on. But ideally, those that are vulnerability testing embedded devices will already have a device in mind that they want to test, so they wouldn't have to go through this process. But for our sake, this is what we did. We developed a list of about 300 embedded devices, all different kinds, to pick one to test our framework. Some of the key considerations when you're picking a device to test is that you need to have access to the physical device. You need to be able to buy it. Otherwise, you can't do any of the hardware analysis if you don't actually have the device itself. So ensure that that is something that you can do. And you need to have access to the firmware, because how could you test the firmware if you didn't have it? So you should also consider the number of firmware versions. Hopefully there's a couple. Hopefully they've been updating their firmware. The availability of this, you need to have access to these files, whether that be publicly available on the vendor's website or you know somebody that can maybe get you the firmware files. And if the firmware is still being maintained, hopefully they have a version that's still being updated. But if it's no longer being updated, that's something that you should note in your vulnerability research, because then it means that those vulnerabilities will remain present. The next step was information gathering. The purpose of this step was collecting information about the past and present vulnerabilities about the device in question. We also looked at similar devices from the same vendor and then vulnerabilities and exploits around that vendor entirely. That should have said 2 steps, not 3, but it's actually 2 steps. So aside from identifying everything with the device in question, you should identify all of the vulnerabilities and exploits, past or present, with devices similar to that from the vendor, all of them that vendor makes. And then obviously identify and make note of all the exploits, if there are any, which hopefully there are, make your research a little bit easier, and keep note of all of that. There's many internet resources, as I'm sure all of you might be aware of, Exploit DB, Virus Total, that have exploits for free for testing purposes.
So the next thing we did was like a little bit of firmware analysis, right? So we used two tools to do this. This isn't like an exhaustive list. These are tools that we found to be useful, right? One is an open source tool called Binwalk, right? It's used for analyzing firmware. It's available on GitHub. It's maintained, I believe, still, and it allows to reverse engineer the firmware itself, right? It looks for key values and extracts that. It can extract that content out of there. The other one is a custom developed tool that we wrote because I was getting bogged down with running too many of my own little scripts. So I said enough is enough, and took some time, took a step back, and wrote our own tool, which is also available on GitHub. I will provide a link at the end. But what this tool does, it looks for these key indicators of possible vulnerabilities in firmware file systems themselves. And it also ties in vFeed. It's that excellent open source tool that we integrated into our tool, which is like sort of a correlation database of a bunch of CVE data, exploit DB data, Metasploit data. They're expanding as they go. I talk with the developer all the time. So we integrated in that because it allows for us to, when we find indicators in the firmware, we can then query this database and get kind of a feedback of, like, say, which we'll show you later on, is this binary associated with any sort of CVEs? If so, maybe you should now check that binary on that firmware to make sure it's either at the most updated version or not. That's kind of one of the examples that you'll see later on.
So most embedded devices have some sort of web application interface that they use. It's usually administrative in nature, but when you can't get to a device, which can happen often with embedded devices like medical devices, implants, things like that, the only way to access it is through this web interface. So this is very obviously something that should also be tested when you're testing for vulnerabilities in the embedded device. There's tons of open source free tools that you can use to do these. Obviously many paid subscriptions that you can get. We decided to use OWASP and Nikto to test ours. They were freely available, they worked well in our environment, and basically just did what we needed them to do. Zap is a proxy that intercepts the website request and then passively and actively scans the website for vulnerabilities. And Nikto searches for potentially malicious files, checks versions, and looks for specific issues relating to the versions that are used.
So for mobile analysis, as you know, a lot of devices might have a mobile application they use to interact with the device. In this sense, we're just focused on the Android applications themselves because they're more easy, freely available to download than said iOS applications. Not that you can't do that, but we focused on one aspect here. So we use another open source tool that actually decompiles a tool, right? And an Android application itself is a sort of a zip file container. So this tool, this open source tool, knows how to read the internal files and extract everything out of there. And then again, we use the tool that we developed to then run on that expanded directory that is now a bunch of files from the Android application. So then the next step is that since you have physical access to the device, you should take, what you can do here is 5 additional steps to do hardware analysis, right? So at minimum, you can identify all the markings on the device. What's on the outside of the case? Is there hardware versions? Is there regulatory information? Is there Wi-Fi passwords, right? Is it what firmware there is, what MAC address, things like that. And then since you have the device now, you can open it up, right? This is a little more advanced, these next few steps, but there's really pertinent information you can gather, right? You open it up, you look at the printed circuit board inside. What components are on it? Identify those components as best as you can. And then you look for data sheets from those components and try to identify pinouts, right? For the next step, which is then to try to dump the actual firmware from the device, right? So if on the back of the device, it might say that this has installed with this firmware, right? Now you can either verify or not that that is actually installed in the device. And then you extract the contents, just as we mentioned above, using Binwalk, and then we run our tool Trauma on it as well. And then the last step is then now you can compare multiple versions of firmware, right? If the vendor has their firmware on their website, you can gather this firmware. Now you can compare it to what's actually installed on the device and look for comparisons. Are they updating their versions? We'll talk about what we did later on in that. And then it can be a little cyclical here, right? You can kind of go out and do more open source research based on what you found, right? And in this sense, we're kind of just looking for the flash component, right? But obviously, there's going to be many more components inside the device, right? There might be a Wi-Fi chip, some kind of Bluetooth communication, and other RF things. But in this case, for our framework this time around, we're just looking for the flash component, right?
And then, obviously, at the very least, we're going to do some vulnerability analysis. We broke this down into 2 different steps. Starts with a manual review of the firmware update for patches. So you should have this entire list of vulnerabilities and exploits for the vendor, hopefully for the device itself, and comparable devices from the same vendor. So you're reviewing these firmware updates to see if these vulnerabilities have been fixed, in what version they were fixed, so then you can go through and test if they were actually fixed. And then you can test the actual exploits that you found for these devices against the device in question too. You should test all of them, even exploits for similar devices that aren't the device in question that you're testing, to see if there's any overlap, if there's crossover. If a vulnerability exists in one device, similar device from the same vendor, does it exist in the other one? You should obviously always take caution when downloading exploits, and it's highly encouraged to review the exploit code before actually testing it. Disclosure really depends on the vendor that you're working with. Ideally and hopefully, they will have a disclosure process already set out themselves, usually just something on their website you can submit and say, hey, I found this, and go through them. If this doesn't exist or you can't get a hold of the vendor, obviously you can follow the CERT guide to coordinated vulnerability disclosure and submit it to CERT and go through that process. So to test our actual framework, we did it on the D-Link DCS 935 HD Wi-Fi camera. Ample amount of testing has been done on D-Link routers, which I'm pretty sure we're all aware of, but very little testing has actually been done on any of their Wi-Fi enabled or embedded devices. So starting with the Curation, how we decided to pick this camera. So we compiled this list of all these devices, all the information about them, prices, firmware availability, if it's still being maintained, all that fun stuff. So we decided to go with D-Link because their firmware is freely available for download on their website. We knew that we would have no issue getting their firmware. This camera was also relatively inexpensive, so we knew we would have no issue getting the physical camera itself. We tested 5 different firmware versions for this camera: 1.04, 6, 8, 9, and 10. So once we decided on the camera, we did ample amounts of research on vulnerabilities and exploits that exist for that D-Link camera and other D-Link cameras. We had got 16 different current vulnerabilities with their CVs, vulnerability numbers, Metasploit modules, exploit database exploits, all that fun stuff. There were not actually any that existed at this time for this camera in particular. So all of the vulnerabilities we were able to find just in background research that currently existed and had been disclosed were for other D-Link cameras. Some of these included remote code execution, remote access, unrestricted upload, cross-site scripting, information exposure, denial of service, directory traversal, and cross-site request forgery.
So for the firmware analysis part, we focused on the newest available version at the time of writing this paper and presentation that was available on D-Link's website to focus on our analysis. So we used binwalk, right, to extract the content, to look at the content of the firmware itself. Ideally, like the best case scenario is our file system underneath, right? Binwalk's able to define that and extract that content from you. Sometimes there might be a file system. It might just be a bunch of files, right? There's other times where it might just be a binary, but in this case, we hope that the binary, the firmware itself, has a contained file system. In this sense, one of the known embedded file systems is a squash FS. There's a few different types of embedded system file systems that you can find on devices. We list those in our paper. But in this sense, we knew there would probably be a squash FS, and there was, and it was able to extract that content. So once that content was extracted, that's when we ran our tool that we developed. So in identify the indicators, it identified 2 files of interest, and it also identified a version of BusyBox that was out of date that contained vulnerabilities itself. So what are files of interest? In this case, these files contain a lot of product information that would actually expand your vulnerability research and analysis as far as like pin information, more information that was on the back of the camera than there should probably have been, right? So this information was either maybe left behind, not meant to be there, should have been cleared out before it was uploaded, to the image itself. Who knows? But it provided me and us more insight to then do further analysis and looking in the different areas. And then, since using the vFeed integration with Trammel, we were able to say, okay, we identified that there was a BusyBox binary on the file system. Now run that against this integrated database and then tell us if there was any vulnerabilities for BusyBox. Well, there is. And then we were able to then go and look at the version that we have on this file system and compare it to what's the most updated version of BusyBox, and found that we have an out-of-date version on the most up-to-date software, and this out-of-date version has known CVEs for it, right?
As obviously I've already discussed, you have to test the web application interface. So we use two different tools, as I said before. OWASP Zap we used to spider the web page and perform active and passive scans against the web interface. I found 4 different findings, 2 that were really of interest and 2 that are more related to a best practice. They didn't have cross-site scripting protection enabled, and the X content type header was missing. This header just prevents content sniffing from a third party. So these are kind of hard to do on a web administrative interface because I have to already have administrative access to then get to this point to do that. So these 2 vulnerabilities were more of a best practice. We did find 2 vulnerabilities that had not been previously reported and that were novel vulnerabilities, and we've submitted that to the vendor website, which I will talk about later. NICTO confirmed all of our findings, almost all of our findings with OWASP Zap, which is why we use 2 different tools to make sure that they found the same things and that this was consistent. It did find 1 additional vulnerability, likely because NICTO asked for the administrative login information, and because we happen to have it because we made it, we figured we would give it to it and see if it found anything once it was authenticated. So it did find 1 unique result because it was authenticated, which was this cross-domain XML file, which is part of Adobe Flash. It has a wildcard entry, which means that any trusted website can view user information on this administrative portal. So if you compromise the trusted site, you can use that trusted site to then get user information from this target site.
So we were able to download this specific MyD-Link Lite application that was recommended by the actual D-Link themselves from the Google Play Store. We decoded it using the APK tool and then ran our tool against it. And in this case, we didn't find any indicators that were vulnerabilities in any sense. So next phase is the hardware phase, right? So this is broken down in those 5 phases. So the first one was identify the markings, right? So there's numerous markings on the back of IoT devices, specifically cameras in this case, right? So you can see here there's a list of different information that was valuable, right? Hardware versions, MAC addresses, regulatory information, SSID passwords, serial numbers, things like that. What I'm looking for in the case is regulatory information, right? So this is information that if it has radio frequency communications on the device, they have to register the devices in said countries, right? You have the FCC in the States, you have the IC in Canada, Europe has one, and China has one, right? So they're registered with these devices. These databases are freely available, and when they register with these devices, they sometimes upload documentations to these databases, which then can provide you more information, right? It's usually a picture of the device. You can verify that the device you have is the one that they registered. Sometimes, if you're lucky, they take pictures of the inside of the device, right? See the PCB board. In this case, they didn't. But this is where that cyclical information happens, where you can gather more information, then go back and do more research on what you found. So once we popped it open, the device, and looked inside on the printed circuit board, we identified a couple of the CPUs that they had, a couple different memory informations. The Skyworks is actually the Wi-Fi chip itself, but we were specifically looking for the flash component, which then we identified as one of the Micronics flash components. So then the next step is to dump that flash off that device. When I mean dump that flash, is to actually extract that content that's on that chip specifically from that device. It's a little more advanced process. However, it's sort of straightforward once you got it done. in our paper, we didn't get explicitly into how the step-by-step it does it, but if anybody has questions, I'm happy to go into details about that. But we use a bus pirate, right? A Linux VM running flash ROM, right? So a bus pirate it communicates with different electronic devices. Flash ROM is a open source software that allows and it understands how to read different flash memory components from devices themselves. So using these two components, we're able to extract the firmware from the device, and because on the back of the device it says that this firmware on there is version 1.04, that's what we label that firmware version. And then it's like, okay, now we need to do that step we talked about earlier. Now we need to look at that firmware itself and then extract the contents and analyze it. And we did the same process that we did from the one that we found from the vendor's website here, and then we extracted the content. We found that it too also had an old version of BusyBox that was out of date. So this device that you get day one that you plug in, most likely it's going to say we want you to update the firmware, but say you say no right now, you're already like way out of date with the BusyBox. And if anybody doesn't know what BusyBox is, it's sort of like the utility tool component that runs all the commands inside the firmware itself, right? So it had identified 6 CVEs. Our tool identified 6 CVEs that it's using specifically for this version of BusyBox. However, luckily at the time there's no exploits for this, these CVEs, right? But that doesn't mean that the device isn't still vulnerable. It just means that no one has publicly, made an exploit available for said CVE. And the last part, we then compared, the files from the version we extracted from the device, the earliest version of the website, and then the contents of the device and the most recent version of the website. We saw very little sharing, which that could tell us that, yes, they are updating their firmware from version to version. However, we only did a comparison on hash values, right? So as we all know, all you have to do is change 1 bit. The hash values are different, right? So there's some more testing to do there to actually see how much is actually shared. However, the most common files across all the firmware that we found and the one we extracted from the device is that shared library object files, right? Or shared object library files. Now, why is this sort of interesting, right? Is that if a vulnerability exists for one library file, it's going to affect all versions of firmware, right? So you can see the impact it has there.
As we discussed before, the researcher should manually review the firmware updates, and I say manually because usually they just release them in release notes. It's like a nice little PDF that says, hey, here's what we updated and why we updated it. And unfortunately, I didn't find a better way to do it other than just manually reading it. So this showed that the 2 new vulnerabilities that we did find that had not previously been reported had never been reported to them and had never been patched because they weren't available in the release notes, which furthered our idea that they were truly new and novel. We attempted the known exploits against the devices, 16 different vulnerabilities, some with exploits, all different model cameras, not the one we're testing in question. So they did not return any results, and that's not to say that our camera in question doesn't suffer from the same vulnerabilities as those that we found in other cameras. Those exploits could just not translate exactly to our camera in question. And as we discussed before, we're following the disclosure process with the vendor because they do have a disclosure process that is very clearly laid out. So we have contacted them, and it's located very, very easy to find on their website. So some future work and improvements that we could do for this is applying this framework to other embedded devices. We could apply this to other D-Link cameras because the purpose of this framework is to create results that are comparable. So we could apply this to other cameras, compare the results with this. We could apply it to different vendor cameras to continue that process, or we could just apply it to totally different kinds of devices. It doesn't have to be cameras. We could further this by doing that. We would also adjust our analysis environment because our environment wasn't set up adequately to completely set up these devices because D-Link is a little odd in their requirements to set something up.
So in addition, we'd also like, this is a framework that's supposed to be evolving, right? So we know that there's RF analysis done. What I mean by that, we didn't do any Wi-Fi analysis, Wi-Fi testing, things like that. obviously with a new crack attack right out there, like that's something we could test as well. It should probably most likely be vulnerable, but other Wi-Fi testing we can do, Bluetooth testing, advanced hardware analysis. I mean, in that sense, is like change firmware, see if we can upload our own version of firmware to the device. Is it doing some kind of checksums against the device? If a device allows you to push your own firmware to the device without looking at checksums, we have bigger problems to talk about. So it would expand the analysis there. And then specifically diving into like looking at the explicit binaries on the device, right? A lot of vendors produce their own binaries to use and things like that, and actually looking at doing some reverse engineering on those binaries. Are those binaries themselves vulnerable? They're different, built on different operating systems than your typical, Intel, right? So there's a lot of people out there doing ARM, but not many people doing MIPS out there right now. So there's some binary analysis to be completed there to add into our framework at a later point in time.
So brief conclusion about everything that we just talked about. We developed this framework to create a universal, holistic, macro-level approach to embedded device vulnerability analysis. We want other vulnerability researchers to be able to use this to ensure that their analysis is complete and thorough, and at the most basic level, they have at least touched every single part of this device. We tested this on a class of embedded devices, a Wi-Fi camera, and found vulnerabilities that had not yet been published. So this helped us further prove that our framework does work, and we were able to find things that no one else had found yet. We developed an open source tool, Trommel, to help other researchers in this process. And we expect this framework to not only expand with our future work, but with the evolution of embedded device landscapes. This is a living, breathing document. We expect different parts to be added to this. Different devices have different needs, and we expect to expand on this in the future.
That's it. So if anybody has any questions, comments, concerns, unfortunately, the paper was supposed to be published today. However, our tech editor got in a car accident last week, so that's understandable delay right there. However, the tool is available right there, right now, to use. I'm open to feedback. We're open to feedback. That's also living and breathing too, right? So I'm already have comments to update things and improve upon it. And know that it's analyst code, right? This isn't development code. I'm not a developer by trade. I can develop, but I write analyst code, meaning that it does what it needs to do and works as well as it needs to work. That's what I mean by that, right? So, but yeah, we'll hopefully have the paper published within 10 days or so. We're in the final stages of editing. Like I said, given the circumstances, I couldn't harp on him, and there was no time to actually get it done. But yeah, that's how you can contact us. Any questions from the audience? We have, I think,
Plenty of time.
10 minutes. I think we left. I think
Yes.
we got it perfectly. Yep.
When you're extracting a flash, are you doing that on a port on the device, or are you actually putting connections on the chip?
Yeah, so he asked, when I extracted the flash binary from the device, how am I doing it? I'm actually connecting to the actual pinouts, right? So when looking at the components inside the printed circuit board, ideally you want to try to find the data sheets for that actual chip, and then you can figure out what the pinouts are. And the bus pirate works so nice and freely with like the sort of pinouts, right? So I was able to connect to those and then pull it from there. Great. No other questions?
We'll be here.
I think there's another talk at 10:30, correct?
Yes, I'm sorry. I apologize.
That's fine. We were really fast.
Well, thank you very much.